pipes that are connected in series before we discuss branching pipes and pipes that connect reservoir. Okay, so the figure here depicts the energy grade line and the hydraulic grade line. So reviewing, our energy gradients are always sloping downwards to the direction of flow. So we have here pipes that are connected in series. Okay, pipe 1, 2, and 3. So as you see, they have different diameters, and let us formulate the relationship between head losses and discharges. Okay, so from this point to this discharge end at D, sa pangalanan natin ng A, B, C, D, this is the total energy possessed by the fluid as it enters point A. Now, as the fluid enters point A and travels along pipe 1 hanggang do sa B, the head loss is decreased by an amount which we call the head loss, frictional loss. Okay, the frictional loss along pipe 1, so that is HF1. So, mula dito hanggang dito, nagkaroon ng drop, a vertical drop, which is equivalent to the friction loss at pipe 1, along pipe 1. And then, as the fluid travels from this point to this point, that has constant cross-section, ganun din, andito na lang yung total energy ng fluid, and then it continuously drops a vertical distance of HF2. Okay, then HF3 is the total loss occurring as the fluid travels from this point to the discharge end. Now, this is disregarding the minor losses due to the changes in the cross-section. So, minor losses lang ang hindi natin isinama. These are the major losses due to friction. So, mula dito sa total energy, as it enters point A, the total energy of the fluid is hanggang dito na lang. Okay? So, the total head loss that occurred is the sum of all the friction losses from pipe 1, pipe 2, and pipe 3, which is equal to the total vertical drop from the original energy gradient to this point. Ito na lang yung energy niya. Okay, so HL, the total head loss from A to D is the sum of HF1, HF2, and HF3. Okay, next is the other line that portrays graphically the potential head. The potential head is the hydraulic grade line. That hydraulic grade line is isang property niya. It slopes downward to the direction of flow, but will always or may rise or drop depending on whether the velocity is bumilis or bumagal. So, at this point, section pipe 1 is a constant cross section. So there is the velocity at pipe 1 will be equivalent to this head, the velocity head, which is constant along the pipe. And then dinugtungan siya ng mas maliit na pipe 2. So siyempre mas malaki yung velocity, so the velocity drops, mas malaki velocity head, so yun. Then dito sa point na to, dinugtungan siya ng mas malaki, pipe 3. So, babagal ang velocity. So, tataas yung ating velocity or tataas yung ating hydraulic gradient. So, sabing ganon, it increases or it drops or it rises depende sa changes in velocity. So, there are two, okay, dito at this point, the only head now that the fluid possess is the velocity head. Kasi ito, kung ating cross-section, ang ating datum ay dito, ito na lang yung kanyang energy left, velocity. Wala siya, discharging into the air, so pressure is zero. And then, we formulated now only two formulas for series. That the discharge is continuous, Q1 is equal to Q2 is equal to Q3, and the total head loss is the sum of all the losses. Okay, so let's have a problem here involving pipes in series. But let's have sa PowerPoint meron na tayong mga samples, but let's have another one here that shows you how the energy and the hydraulic gradients are drawn. Okay, so the figure here shows you a reservoir at A, and from the reservoir is connected a pipe 12 meters long and 200 millimeters diameter, and it is the reservoir is supposed to supply a fluid, supply water to this point. Okay, the discharge end being a nozzle that is 38 millimeters, but the nozzle is higher in elevation than our reservoir. So what is needed para mapatuloy-tuloy ang flow ng tubig hanggang dito sa elevation na yon is to use a pump here. So ito yung figure natin. The pump efficiency that is used to transport water from the reservoir to the nozzle is 75%, which will discharge 32 liters per second. Now, in this problem, we will be required to consider the minor losses. The minor losses being the loss due to the change in the velocity from 200 millimeter suction pipe to 150 millimeters at the discharge end up to the nozzle. So the problem here will require you to draw the energy gradient and to find the input, the horsepower input of this pump. Okay, energy input of this pump. So ito yung mga given, efficiency of the pump that will be used is 75%. The discharge, yung discharge through the nozzle is 32 liters per second. The pipe will have a friction factor of 0.024. The coefficient of contraction, kasi nag-contract siya from 200 to 150, is 0.5. The coefficient of velocity, which we are going to use for the head loss due to the change in velocity, is 0.95 through the nozzle. So, let us draw muna natin yung energy grade line. So, this is the total energy. The height of water in the reservoir is 1.5 meters with respect to our datum. So, gawin na natin datum itong pump. So, it's 1.5 meters. Okay, and then susuplayan yung point na ito through the nozzle, which is 15 meters. So, if this is our total energy, the hydraulic or energy gradient will slope downward towards the pump. So, ayun yung slope downward towards the pump. At yung slope na yon ay mangyayari throughout the length that is 12 meters. So, ayun. So, meron tayong HF1. Ayun, HF1. Along pipe 1. And then there is an additional energy, an energy added by the pump. So, yung ating energy will rise kasi meron tayong added energy from the pump. Okay, supplied by the pump. So, ito na yung energy natin. Okay, and then mula dito hanggang dun sa 0.3 na yon, bago yung nozzle, the energy gradient is dropping a point which is equivalent to HF2, pipe 2. Okay, and then we consider the minor loss due to contraction from 200 to 150 mm. Ayun yung isang head loss. So, and then H of N. Ayun, bumagsak ng konti yung ating energy because of the loss due to the contraction of the nozzle. Okay. So, yun yung, then, ito, pinakita lang natin that there is the velocity in this pipe. Ito yung space na yun. Ito yung space na yun. Then, applying Bernoulli's equation, ayan yung ating equation. The total energy at the reservoir is equal to the total energy at the discharging nozzle plus the head loss that occurs mula dito sa point A hanggang do sa discharge end. Okay, so ito ngayon yung head losses. Okay, then applying again the continuity of flow it discharges 32 liters per second. So, yun ang discharge sa pipe 1, yun ang discharge sa pipe 2, yun din ang discharge sa nozzle. So, yun yun. So, using this relationship of continuity of flow, makukuha natin yung velocity at point 1 or pipe 1, velocity at pipe 2, the velocity at pipe 3, which is the same as B2, parehas lang naman siya. Siya yung inlet ng nozzle, and the velocity at the nozzle. Okay, so makukuha na natin. So, ayan yan. Now, the Bernoulli's equation, okay, zero na natin yung velocity at A. We already know the reason why. Okay, the pressure at A, zero rin yan, atmospheric. The pressure at the nozzle at the end, the discharging nozzle, zero din. If this is our datum, yung ating A is 1.5. Ayun. Mamaya ilalagay natin. Okay, and then we will find HA. Zn is 15 meters from the datum. The head losses from A to N can be computed. So, eto yun. The contraction, head loss due to contraction, given yung coefficient of contraction is 0.5. Again, any change in velocity, any change in the direction of flow is equivalent to a minor loss due to contraction to enlargement. So, again, ang naapektuhan nun ay velocity. Kaya velocity lagi yung the coefficient of contraction is 0.5 affecting the velocity head at the nozzle. Okay? So, ayun siya. Contraction mula dito sa inlet hanggang dun sa nozzle. So, gamitin yon. Okay? 0.5. Ito pa. Okay? Velocity is 28.22 plus over 2g. That is 0.027. Okay? The head loss at the nozzle, okay, at the nozzle is asan yung velocity niya? Ayun, 28.22. Okay, ito yung formula natin dun sa formula natin ito dun sa orifice. Okay, in terms of the velocity, the coefficient of velocity, the head loss is, ayun, kaya, ayun, substitute, it's 4.38. Okay, so the other head loss that is due to contraction is when the pipe changes from pipe 1 connected to the inlet of the pump to the discharge end, which is pipe 2. So the velocity head due to contraction is B2 and the coefficient of contraction is 0.5. So this is again a head loss due to contraction of the pipe. Okay, pipe 2 has velocity of 1.81 squared. Okay, the coefficient of contraction is 0.5, so we get the value 0.017. The head loss due to contraction from 200 mm to 250 mm. Now, the major losses are the losses that occurs along pipe 1 and along pipe 2. By the Darcy-Weisbach, it is F L over D times the velocity head of the pipe. So, we just substitute the value. F is 0.024 given. Pipe 1 has a length of 12 meters and a diameter of 0.2 meter. The velocity of flow in that pipe is 1.08 squared over 2g. So, we get this value for the major loss. The major loss occurring at pipe 2, which is the pipe connected from the pump to the discharge end at the nozzle, is 150 meters long and diameter is 0.15. So, the head loss is 4.01 for pipe 2. Now, accumulating all these losses, friction loss at pipe 1, pipe 2, the contraction, the head loss due to contraction from the inlet to the nozzle, and then the contraction loss from the 200 to the 150 millimeter pipe, and the head loss at the nozzle. In-accumulate natin yan, so the sum is 8.52. Now, going back to the Bernoulli's equation, ito yung kanina, Bernoulli's equation, so wala siyang velocity head at reservoir and the pressure head at the reservoir, kinancel na natin. So, ito na lang, okay? Nakuha na natin ito, the total head loss. So, what is the energy energy supplied by the pump is 62.61. Yun na lang yung energy or head added by the pump. Now, we know from that power, yung formula natin, the power is equal to the discharge, the unit weight of the fluid, and the energy over 0.746 para makuha natin yung horsepower. So, it is substituted. Nagdi-discharge daw yung nozzle ng 32 liters per second. This is the unit weight of water, the energy. Okay, the energy supplied by the pump over 0.746. So, this is in kilowatts para divide lang natin ng 0.746 para maging horsepower. Okay, so yun yung P. Now, P is, ito yung power input nung kasi nanggaling do sa energy added. So, this is the power input of the pump. So, what I mean, power output. Okay, ito yung power output. So, kuhanin natin yung input. Okay, the efficiency of the pump is only 0.75. So, solving for the input is the output supplied by the pump, okay, over the efficiency 0.75 para maging kilowatts. Ito ay horsepower. Para maging kilowatts, ito siya. Okay? So, 26.21 kilowatts yung horsepower input nung the kilowatt power input by the pump. Okay?